the Zoom and.
Well, welcome and thank you everybody for joining today's C2 Smart webinar. I'm Lizzie. I'm a research project manager at the center, which is a US DOT designated Tier 1 University Transportation Research Center tasked with leveraging recent advances in big data and technology to solve today's most pressing urban mobility challenges. And today we are joined by Professor Shenhao Wang, who will talk on his deep choice model presentation. So some quick notes to start. We'll be recording this session and then uploading it to our YouTube channel. So I encourage everybody to participate through posing questions to our presenter. You can do so if you're here in person, obviously, or by pressing the Q&A button within Zoom. And we can read out the questions at the end of the presentation. So today's presenter, as I said, is Professor Shenhao Wang from the University of Florida. He's an assistant professor and director of the Urban Artificial Intelligence Lab at the University of Florida, and is also a research affiliate to Urban Mobility Lab and Media Lab at MIT. And with that, I hand it over to you guys over there. And yeah, you're ready to get started. We're ready when you are.
Hello, did you hear me?
Yep, we can hear you and we can see your screen. So we should be
All right, good. All right, thank you so much for having me here, and sorry for the delay. I'll try my best to be on time, but you know, it's sometimes not a personal problem, but like systematic issue, and we all try to address that. So today, I changed the title a little bit, but essentially they refer to the same thing. I talk about the deep choice models. As you can see, it's about the choice models, but it also have a lot of deep neural network, deep learning component there. So here is the outline today. So our target to have like 40 minutes presentation, and then at the beginning, 5 minutes, it will be just a background, and then I'll talk about using about 15 minutes to talk about deep neural network for choice analysis. So that's kind of my past work, all published between around 2021. So you can find those papers in TR Part B, Part C, those journals. And then I'll talk about a recent work we call deep hybrid models. Basically try to use our existing framework and incorporate unstructured data like urban imagery, still to understand the individual decisions. And last one, I just summarize the findings and I'll talk about the implications. And so first of all, I think I presented this part twice in different contexts. So how many of you have heard about this? The second one, somehow? All right. Then I could elaborate on that. Just some word like this, some repetition, and then you might be bored. All right. So first part about the background. So what's the exact research question I'm asking? And then what's the exact problem we're trying to solve? So the question I try to deal with is the kind of a classical choice analysis with application in urban mobility. So this just shows a kind of classic question. You know, in our textbook is about 12 mode choice. But one person just need to choose between, let's say, two alternatives. One is driving, could be typically to be more expensive and faster. But it could be like choose the public transit. In many cases, it's like much cheaper, but it takes a longer time. So it's just a classical research question, and we need to understand the trade-off between dollar values and their travel time. And then in that, we try to understand which the output is the decisions you choose either automobile or bus. Okay. So this is actually an old question, right? Because this person, Daniel McFadden, developed a discrete choice model framework for the past about 5 decades. Right. In that kind of standard framework, there are 4 components: decision maker, their individual specific attributes, and then those alternatives. What's the alternative set you want to choose from? And then alternative specific variables. That's like price factors describe each individual alternative. And then last one is decision rule. The standard framework is using utility maximization, the random utility maximization, but there are many other rules. In the end, it comes to this like softmax activation, this function, we call it softmax activation function of the deep learning thing, but it just takes this form, and then we use that to model the choice probability among all the alternatives. So when we think about these days, right, how do you analyze this question? You have another approach, we call it let's call it a black box approach is just treat this kind of discrete choice task as a simple prediction task, right? Because you have simply the inputs and outputs. The inputs include socio-demographics and those alternate specific variables, and the outputs is just your individual decisions, which means that if you just open your machine learning textbook, just a table contents, to look at all those machine learning classifier, you could apply any of them to this discrete choice setting, and then get some prediction performance, and which is typically higher than the classical discrete choice models. In other words, these days we could observe a tension between the classical discrete choice model and the deep neural networks, right? On the one side, we have so-called theory-driven models. They're based on random utility theory, and it also has a deep root in the microeconomics of those models. We specify the utility functions, and then in the end, we try to understand why people make decisions. But on the other side, we have all the machine learning models, right? We call them data-driven models. One example is just deep neural networks, and typically we could gain very high prediction accuracy. And in fact, when you think about the tension between these two groups of thoughts, you could think about many perspectives, right? For example, from the deep learning, the machine learning community, they could simply criticize other side by lacking some prediction accuracy. Right? But meanwhile, the other camp could just criticize the machine learning side, saying, well, you have some prediction performance, but meanwhile, you don't have a lot of interpretability. But this is just prediction and interpretation are two things that people talk about the most frequently, but there are many other aspects, right? Like robustness or generalizability, those things. So fundamentally, we need to answer this question, right? How to really reconcile the tension between this model-driven approaches and then this data-driven approach. I believe this is a very general question. It's not only just in our field, like transportation or like smart cities, we need to address this question, but across all kinds of disciplines. When we see the power of AI and deep learning, all the disciplines like in chemistry, biology, they all try to deal with this question. So today I just demonstrated this how to address the question in our field. But I believe a lot of insights can be widely applied to many others. So let's just move to the second part that we call deep choice models. I try to establish a new theoretical foundation for behavior analysis with deep learning. So there are two papers in this part. The first part, first paper is just we start with this black box model and just saying if we have very simple deep neural networks, to what extent can we interpret those economic information from the so-called black box model? All right, so we go from the black box to the, let's say, glass box side. And then the other question is, if we have some behavior information, right, it's a glass box model, so we have a lot of insights. So can we use some of our behavior insights to design new deep learning architecture to improve the prediction, robustness, or even interpretation? Okay? Just go two directions, and then I present one paper for each direction. So for the first question, it's essentially a question whether deep neural network is a black box and to what extent can we interpret them. And the answer, surprisingly, is actually we could get all the economic information from deep learning. The reason is that actually discrete choice model and deep learning are very similar in terms of shared utility interpretations. So if I try to just visualize the discrete choice model, actually you could visualize as a very sparse and shallow one-layer neural networks as such. So it has two components. The last layer is just a utility comparison. You compare the utility values, and all the ones before this layer is actually here's the one layer. It's just a utility specification. We specify utility function and we compare. Actually, deep learning, although it has very complicated structure here, right? In the middle, we could still treat them as two parts. The last layer is just compare utilities, and then all the layers before the last layer is just utility specification. And I cannot prove it by visualization. It's not a very rigorous way to do it, but you could check the paper. There are a couple of papers discuss why it is a valid argument. But based on this similarity, there are interesting things. One is, of course, utility specification and comparison that exists in both discrete choice model and deep learning. And the second is, once you see the similarity, actually there are two functions. One is a utility function, and the second is a choice probability function exist in deep learning. And because it exists, we could just leverage these functions to get a complete list of economic information. So basically, I just summarize all the economic information from our textbooks and just try to see, can we get those information from deep learning? And when you look at the formulas, you can see we only use two functions. One is this utility function, and the second is choice probability function. And then when you have these two functions, you could get all the economic information. So in the paper, we just present all the economic information, how to get them, what's the pros and the cons of the information from deep learning. But here I just give you a short example. The first example is those elasticity values from deep learning. Now, when you take a statistic class or discrete choice model class, one input and output you get from the statistical package are just this like coefficients, elasticity coefficients, right? And here we just demonstrate that from deep learning, you could get very similar coefficients, and for our economic interpretation. And then when you look at this table, each rows are just those input features, and each column are these output features, each alternatives. And when you look at the main diagonal, you can see I said the first one, the working elasticity regarding to with respect to the work time is negative, right? Which means that when you have longer working time, it's less likely for a person to work, right? And then look at the main diagonal, they're all negative values, which means that deep learning could not only give us some values, and then for many of those values, they're very valid, very consistent with our behavior intuition. The second example is a substitution pattern from the alternatives. Basically, the idea is when we change one input variable, and we try to observe the change of market shares for each alternative, because we know the choice probability for each individual when they add them together is a market share for all the alternatives, right? So here the x-axis is just a driving cost. When we increase driving cost, you can see here the choice probability of driving is consistent decrease, right? This is the discrete choice model. We use the multi-node logic model as a benchmark. So here it just shows that when you use the discrete choice model, this substitution pattern is very regular, right? It's smooth and go down for the driving, and for the others, it just goes up. And actually, it's kind of the standard S-shaped curve, the kind of technology adoption curve. And then, but when you cut like part of that, and it looks like this, right? When you look at the deep learning, it could still give us some substitution patterns, right? So when you increase the driving cost here, you can see, roughly speaking, the driving probability still goes down, and all the others, roughly speaking, should go up. But meanwhile, we could see there are a lot of irregularity in this part, right? So because at a certain point, when we increase the driving cost, you can see the orange line, which is public transit market share, also goes down. So it's really not like consistent with our behavior intuition. So which means that somehow just suggests that this choice model is very regular, shows very regular behavior patterns. But for deep learning, it could provide us some behavior patterns, but it might be too complex and to show a lot of irregular behavior patterns. I want to map this idea to some standard static learning theory, which I believe many of you must be familiar with. If you take a machine learning or deep learning class, you should be able to see this curve, right? There's like two types of arrows, and you add them together. And the x-axis is just the complexity of the function class, model class. You assume, and the y-axis are the risk or errors or performance, whatever you name it. And then when you think about discrete choice model and deep learning, actually, when they deal with simple data structures, you could treat them as locating on the two ends of this x-axis. Discrete choice models, there are some simple model families, and then when you think about how they model the behaviors, they might be too simple to reflect reality. But deep learning, the problem is the opposite, right? When you think about it, deep learning might be a too complex a model to reflect reality. That's exactly the statistical learning summary for the previous behavior intuition. And when you think about the summary, actually, we follow the same logic to develop models, right? So when you think about how do we develop those discrete choice models in the economics or transportation review, we start with very simple models, multinomial logic model, which was developed in 1974. And then over time, we make it more and more complicated, right? We specify all kinds of utility specifications, the functions, and design more and more complicated nested logic model, mixed logic model, and hybrid models or things. The enriched model try to go from here to the middle, like some optimal point. But when we look at deep learning, the challenges seem to be opposite. It seems to be a too complex model family. So somehow the idea is we try to simplify these models, provide some regularizations to get a better behavior pattern. So which naturally lead to the second question. If we have one piece of a behavior knowledge, we could introduce it as some structural constraint to the model, and we call it like regularization in the deep learning or machine learning community. Then, so the question, the second paper is, can we use the behavior knowledge to regularize deep learning for some novel model design and then improve the prediction, interpretation, and robustness, all kind of stuff. The idea here is really simple, actually. First of all, I just change the visualization a bit. This is another like simple visualization for deep learning. You have like input layers. Here we have alternate specific variables, like k alternatives. So input from x1 to xk, and z just represent the socio-demographics. Right? So it's not specific to alternatives and their input. And in the middle, we have m like middle layers, just deep learning, the standard artificial neural networks. And the outputs here, utilities and softmax. We describe why the utilities. I think we could call them utilities in the previous paper. And the idea is, can we design some network so that the utility for each alternative is only is a function of its own attributes. So the way to do it is just really to divide this whole neural networks into kind of k subnetworks. So there are utility. So there is a utility value for each alternatives, and then when we divide the networks, and input are just the alternative its own attributes, and you have several subnetworks, and then the utility of alternative k becomes a function for social demographic and its own attributes, right? So when you look at the design, there are two implications. The first is sparsity. So when you look at one layer here, you can see the weight matrix for the fully connected neural network is a full matrix, right? But when you look at the weight matrix for the ASU, that's the name. It alternate specific utility deep neural networks. Only the main diagonal has values because the main diagonal represents a connection within each subnetwork, but the off diagonal, those values are all zero because across the subnetworks there are no connections. Right? So basically, it's a kind of network perspective here. And the second is through this ASU this structure design, we introduce something called independence of irrelevant alternatives in this deep learning architecture. How many of you are familiar with this constraint? So it's kind of one standard kind of assumption in the discrete choice models. Here is just a kind of summary. So basically, we're thinking about the two like choice situations. In one case, we choose between like two alternatives, right? And in another case, we add one more alternative. But this IA constraint basically says that when you add this one actual alternative, what's called an irrelevant alternative, the ratio of the two choice probabilities remains constant. It's not influenced by these actual alternatives. So you can see the ratio here, if it is a 1-to-1 in the market share, and you add one more actual alternative, let's say working, the ratio here between the two existing alternatives are still 1-to-1. So that's a constraint. So actually, when we introduce this ASU DNN architecture, it satisfies this IA constraint. The reason is actually pretty simple. So when you compute the choice probability ratio of two choice probabilities in the default neural networks is a function of all the alternate specific variables. Right? But when you have this architecture, as you can see, the ratio of two choice probabilities is only the function of the two alternative attributes, right? Which means that when you change the attribute from all the other alternatives, this value does not change. Right? So there are a few consequences. One is about the prediction side, because we introduced regularization, and then what we found is with this simpler architecture, this kind of behavior inside the regularized neural networks, we get higher performance in both the validation and testing side. And also we try the two data sets, and it's very consistent result on two data sets. But more interesting is really not about this prediction performance, but this behavior inside, because I kind of alluded to the fact that we think about neural networks, it might be too complex model to reflect reality, right? Because there are some irregular patterns here. When you think about the discrete choice model, it might be too simple to reflect reality. So through this ASU DNN architecture, we reach a very interesting mixture. So if you look at the substitution pattern here on the right-hand side, you can see as a local structure, it kind of maintains the complexity from the deep neural networks, right? You could see a lot of like irregularity locally. But when you look at the overall structure, you can see when you increase the driving cost, roughly speaking, only the market share of driving always decrease. And then the market share of all the other alternatives always increase. This overall structure is very similar to the multi-node logic model, and actually is a natural consequence from this IA constraint. So when you have IA constraint, when you look at the overall market share, the change, it will look like this. And in ASU DNN, it will look like this. So it really deals with a lot of irregular patterns from the deep neural networks. Right. Any question? So if you have any question, and just feel free to interrupt me. And
well, I mean, so that constraint, the IAA, that reflects simplicity of the ML model, right? And it's not necessarily something you want to have.
exactly.
Yeah. So in that case, you're trying to mimic that.
So that's a really good question. There are two ways to answer that, right? So IA is, we call it the axiom, but sometimes we just say it's an assumption, right? Like after 1974, like people challenged that by enrich, like developing the next larger model. So this assumption could be right, could be wrong. And these days people believe that's wrong. So it could be a too strong a constraint I imposed in the architecture. But whether it's too strong or too weak, it depends on that, like empirical test, like performance test, or like some intuitive like a behavior examination. So that's just a demonstrate through the prediction performance and this economic patterns, it's effective, like to provide us a different substitution pattern. But meanwhile, it's possible to relax this constraint a little bit, right? Introduce something like the next larger that kind of structure. If we believe the alternatives has like community-based structure, and we could introduce those like overall structure constraint. So this is only one example. It's not necessary. This IA is not necessarily a right assumption.
Have you compared with like mixed logit or other objectives like random regret minimization?
No, not yet. Yeah, this is just one paper.
Yeah.
So I think the reason why we didn't compare this model to mixed logit is a mixed logit model is essentially it has a lot of like randomness. It's kind of probabilistic modeling approach, right? If we think about mixed logit models, this error times, I move that to the like coefficient, it becomes some Bayesian approach. And these days we do have the Bayesian neural networks. And I think we want to compare to mixed logit model, and I want to make it a fair comparison. We better have the Bayesian neural network and then still introduce this IA constraint and then do a comparison. And of course, I think it'll be more interesting because the Bayesian approach will have a lot of randomness there, like a model uncertainty and data uncertainty. But here, the deep neural network is relatively deterministic system. So we just compare this to mixed logit model. There's some unfairness there, but people definitely challenge a lot, saying, all the papers published in our field, like, and we just demonstrate the deep learning model could beat all our existing models, while when we like use the existing model, they're just a very simple multi-node logic, right? Without doing justice to the like complexity or richness in discrete choice models. Any other question?
And you're using the same data sets for both?
Yeah, exactly same thing.
There were some questions from the audience, but probably we can wait until the end to go through.
Okay, sure. So these are two papers, just two examples here. Actually, during this in the past 2 years, we published a few papers just along this same line work. For example, in the architecture design, the paper I just presented, we use one piece of behavior knowledge, right, and then design the architecture. But you would say we have so many different insights, and then can we just like kind of easily synergize this model family together and gain the benefit from both sides? Actually, we could do that. We kind of borrow the ResNet, the architecture, and then create a synergetic framework in another paper. It's published in PRB. And meanwhile, people often ask, well, these days the deep learning models is just like playing, the Lego games. You get all kind of different components, put them together, show, hey, we get a higher performance. But is there any theoretical foundation? Like from the statistical perspective, we could analyze better provide some upper bound on the performance. Actually, we could also do that. Provide the paper about using static learning theory to provide some valid bound on the predictive performance. And then there's interesting application, in our field. Typically, in some cases, we have some larger scale data set, but meanwhile, we have the small scale experiment data. And sometimes people call it the review person data versus state person data. Of course, if the second data set come from some survey, and then how to combine them. Right? It's kind of also a classical question. I also designed some architecture, multitask learning architecture to combine them. So there are kind of 3 spin-off ideas, and you could also check. They could enrich the first 2 papers I just presented here. Right. So all the things is kind of published before 2021, and last year I started my job in University of Florida. Naturally, you think about something new you need to work on. So one limitation about all my past work is I kind of simplify the data structure. All the data, I did not elaborate on that. They're just a classical, travel survey data. They are kind of numeric information. But when we think about the revolution from the deep learning and AI, one important thing is they're really powerful in terms of addressing, the handling the unstructured data, images, natural language, graphs. And the deep learning is unique because it's really powerful. It could powerfully address all kinds of data structures. It have an artificial neural network to deal with numeric data. We have CNN for the images, graph neural networks for the graph structure, right? They also have a different architecture for the language model. So actually, we try to really extend it to incorporate unstructured data, in this case, the urban imageries, to understand individual decisions. So I'll present the third part called deep hybrid model with urban imagery. And then specific question is how to integrate those social demographics, those numeric information, and the urban images to analyze travel decisions or any human decision. So the first question is, why do we try to integrate social demographics and imageries in cities? And there are two different reasons. One is imagery is really ubiquitous in any human decisions. So when you think about the driver decisions, of course, you describe this person by its income, gender, its age, but you think about the inputs to that person's decision-making in that specific context, it's always represented by 3D image. You could extract a feature for this area, like this 3D image, and put it simplify it as numeric data. But when you think about the decision context, it's always image as input. And when you think about consumer decision, it's the same thing. Describe the consumer background by those numeric values. But when you think about how this person makes a decision, it's always image as input. So its behavior, it makes sense to incorporate images into this decision choice analysis. And the second is actually image also has economic values, just intuitively. It's still hard to rigorously prove that. But one of my background is urban planning. In urban planning, people talk about all kinds of cities. But when they propose city design, like gradient cities, gradient city, they talk about those social benefits. In many cases, we could really attach a dollar value to this benefit. And we also have the painting. These days, people generate the painting and they try to sell them to the market. And then naturally, it's just attach some dollar values to this painting, especially when they're generated. These days create a lot of controversies, but that's become the reality we need to deal with. So that's why we have this question, how to integrate the numeric data and the urban imagery for individual decision analysis, the improving model prediction and interpretation. So in that working paper, we already uploaded to archive, and there are many components. But for today, I just want to emphasize two things. This is the integration part, how we integrate the two data structures. One is the low-dimensional numeric data. The other is the high-dimensional imagery data. And the second is, once we integrate that, can we still get the economic interpretation for the urban imagery? Can we say something about social welfare, about the dollar value for the images? Whether can we do that? Right. So that's why we designed some framework we call it a deep hybrid model. It's kind of we call it a crossing structure. Let me expand a little bit. So basically, you could see the crossing. There are a vertical axis, and then there's a horizontal axis, right? So we try to say the vertical axis, this line, is more like a traditional models. Here, X represents the social demographic, the numeric information. And then this horizontal line, this is actually an autoencoder structure. You have images, right? You encode the images into a latent space, and you have decoders, which means that for this structure, it has the generative components, could automatically generate images from the latent space. So the horizontal line is kind of deep learning components, right? So the horizontal line has a deal with unstructured data, and the vertical line deal with structured data. So the horizontal line is more like a deep learning framework, and then vertical line is more like a shallow neural networks. And then you could also think about other contrasts, right? The vertical line, you could have the handcrafted features. You believe there are some building environment numeric information, their value, you could put them here. And then you believe there's some other images, not only a satellite image, but all kinds of other images, you could put it here. Right? There are many different ways to enrich the hybrid model. But this is your first perspective. The second is operational perspective. Right? When I visualize that, what does it mean? How we compute it? So we divide it into two components. The first component we call the mixing operator. So basically try to combine social demographic with images in the latent space. And second, we call the predictive behavior predictor. So from the latent space, we try to predict the behavior. In this case, this is travel behavior. So there are a couple of ways to design this mixing operator. Here are just 5 different examples and help us to understand a few questions. Sorry, the title here should be only in total 5 models. The first model is very straightforward. Actually, just removes images. We use the social demographics and some numerical information to predict the trial behavior. It's just a benchmark, right? The pure discrete Charles model framework. And the second is we use only images. And we just remove the numerical information and use only images, and then, of course, embed it in a latent space and do the prediction. And third one is also kind of naive idea. We have the social demographics, we have images. Why do we just concatenate the two vectors together and to see whether we get a higher performance? We have the longer vector. Of course, we need to use the regularizations, L1, L2 regularization, and then, but it could work. So that's another empirical test. Now, fourth and fifth models are we try to. I will talk about the supervised learning, supervised social demographics in the next page. But basically, we try to combine the models, combine the two type information through supervised learning. And then one approach called supervised social demographics, and that is supervised images using autoencoders and in latent space. So with these 5 models, we could answer a few questions. The first is, does social demographic image help us to predict model, right? Predict trial behavior. If the R square of these first two models are higher than 0, and the answer would be yes. And the second is, are they complementary? Right? Because there are 2 different data structures. We want to understand whether the 2 data structures are complementary to each other. Then we will just compare these 2 benchmark models to others. If this our like deep hybrid model design get a higher performance, probably is just demonstrate the complementarity of the answer, the 2 information structure. Then also we have there's a supervision as mixing help. We'll talk about the idea later. And in the end, we just answer whether the deep hybrid model, the whole framework helps. So the supervision as a mixing is the idea that when we have the deep learning, actually in the baseline model, it's automatically help us to mix the information. For example, if you just use images to predict social demographics, actually a lot of people already published this idea, Nature Science paper. The basis is saying when you have the satellite images and then you map them to all the social demographic, income, race, all the information, we could predict them very well. Especially it's very useful in the developing countries when you don't have this like survey-based information. But the other thing is when you have these neural networks using image to predict the numerical information, actually this layer by layer, it demonstrates a mixing between the 2 information, because intuitively the neurons on this side like kind of more similar to the image information, right? So when you get all the vectors on this side and then try to compute some similarity between the 2 information, they should be very similar. But when you go to this side, and they'll become more closer and closer to the social demographics, which means that when you look at this x-axis, you could just design a lambda term saying this is something called a mixing strength. And then you go here and then you could just change the mixture of the information. So this is a simple intuition. Of course, the real like mathematical this process is more complicated, but this is like high level summary about this supervision as mixing this idea. Right? We use that in both model 4 and model 5. A little bit of context for this research, we still use the travel behavior, the travel survey, but for each travel survey, always have the context in Chicago, for all the travel survey, you have location information, like census tracts or the longitude latitude. So we could augment the satellite images to this for all the observations for the X and Y. And then once we augmented the satellite images, we could run the deep hybrid models. So it's a very general idea. Once you have this like a travel survey information with all the high resolution location information, you could do it. Okay. And the findings. So the 2 parts I want to talk about. One is integration, and second is interpretation. In terms of integration, so it's just the 5 models I present. Here I just added the performance R square here. The outputs are just a trial behavior, the continuous variable, so we use R square. And the answer to all the questions I asked actually is yes. Because first of all, the first 2 models get a higher than 0 R square. So social demographic and images both can provide information for travel behavior prediction. And then when you compare the model 3, 4, and 5 to 1 and 2, you could see the higher predictive performance. So which demonstrates that the images and social demographic, they're really complementary information. Right? So which shows the value of the deep hybrid models. And then we look at other questions and then compare model result, we also get the yes answer.
I have a quick question. You're saying that travel behavior is continuous?
Oh, because it's the census tracts are the unit analysis. So in this case, we will have actually two experiments. One is using continuous variable, another discrete.
Okay.
So in both cases, the answers are the same.
Okay, so the 2 different axes are different.
Oh, no, it's the same model, but we try the different experiments.
I see.
Yeah, so we use the sensor track as a unit analysis, and in that case, it's just a mode share as outputs, and then as a continuous variable. We also try to use individuals as unit analysis. And then in that case, it's the log likelihood or prediction accuracy. Okay.
But some of these models, you end up with thousands of dimensions, right? For the latent.
Exactly. The latent space could be very high dimension. So that's why, sorry, I skipped a few things. For behavior predictors, we need to use the hyperparameters like lasso and ridge to control the sparsity. Yeah. So basically, we have to mix those two type of information to latent space. The latent space could be relatively high dimension. It's no longer just like a traditional hybrid model in which it's just one or two latent variables. It's a very high dimensional, and then we use that to predict our behavior. But we are worried about overfitting. So in that behavior predictor, we have the lasso and the ridge.
I also have a quick question. Maybe I missed it, but what exactly we're getting from the urban images? Is it what is shown here as X, the income, education, house?
For image, we just use the raw images.
Okay.
Yeah, we did not try to extract any feature from image, but of course you can do it.
Mhm.
Use a semantic segmentation or other stuff.
How about the size of
What?
We did resolution of it.
I think it's 256 by 256. It's relative. It's all. Yeah, when we collect it, it's a 600 by 600, and then we kind of change the resolution so that we could deal with that of this convolution on that one.
So you're saying that the image use the additional information. What is that information? I mean, raw image.
Very good question. So deep learning, when you just run the convolution neural networks, the deep neural network does not provide any interpretation. So it's just tells us, well, it's highly predictive, which means that for the architecture here, it learns some like automatic learning and some features. But they're like a CV tradition. They'll talk about why they designed the convolution layers such, and they will tell you that like here they will detect some low level of features like the edges or like small areas, and then but here is kind of high level, more abstract features. Like maybe in this case, it's like one neuron just represent there are a lot of green areas here, or another neuron says it's very diverse in terms of the building scales. We don't know, but that's the common belief in terms of that CNS power.
And you're predicting the travel mode, right?
Yeah,
Your
trial
wise
mode.
mode.
Yeah, we really simplify the output side. It's all trial modes consistently throughout this presentation. Sorry, go ahead.
And the features are for the origin and destination?
Yeah, both. Very good question. We kind of concatenate the origin destination without carrying the order of that too much. Basically, when we think about the urban graph, we kind of model it with an undirected graph without the direction. So, but of course, O and D is mean different things. Now traffic flow. So you could treat them more carefully in the different.
So one quick question. This grid is standardized, right?
What?
Is the size is the same, or the grid are same size?
All the grids you're saying the
picture.
picture, yeah.
Yeah.
CT.
If you switch to census tract, then maybe they are different size.
Exactly. Very good question. We try out the zoom levels. So we collect the different zoom levels from the Google APIs. And then somehow there is some trial and error process. And we figure out what's the best zoom level to provide the kind of informative prediction. And I believe to address your question, they're kind of related to the multi-level like image models. People deal with that, like you have images and they create like image pyramid from your raw image, and then saying at the different scales provide different kind of information. It's just the one extra layer to enrich the model. You get to the horizontal line, and then you could introduce a hierarchy structure there, and then saying, okay, latent space will become richer. And I believe that that's a doable direction. Okay. All right, let's move on. I think I need to simplify a few things. Here it just says all the answers. Ask the question, they're all yes, very positive results. All good. And second is one new thing. So the deep hybrid model is a little bit complicated. One reason is we really want to embed the generative power into the model. That's why you have this kind of decoder part. And then once you have a generative model, the power is that this X, Y, and Z they're all kind of old things. When you have the hybrid model, you have latent space, and you could do all the what if analysis, simulation, right? But when you have the generative model, it means that we could do simulation with images. Right? We regenerate images and tell stories with images. So what do we do? We just demonstrated it with an example, just saying, let's say Z is a latent space. It's a very high dimensional space, but reduce it to 2-dimensional. And we choose 3 examples. One is it's called a status quo, the South Chicago. We don't. People often say it's not a good place. It's like very poor. So we try to move, in the latent space, move from that status quo, the South Chicago, to North and Central Chicago. So the status quo is this image, and then you can move to the North and the Central Chicago in latent space. And then we demonstrate in this 2x2, actually, this kind of matrix. So the S, M, and C, so that corresponding to the status quo, the South Chicago, North Chicago, Central Chicago. We could move in latent space and regenerate all kind of images. Right? So which means among the 225 images, the only 3 images exist in reality, and all the other images are just generated by the the interpolation or extrapolation in the latent space. So that's a generative power. But because the deep hybrid model, it has social demographics and trial behaviors, we could tell stories about these images, right? So we could compute the social welfare for these images, attach the dollar values to them, and also demonstrate behavior changes along these directions. So I'll skip the detail here, but basically we could compute the social welfare for all the images and try to figure out the dollar values, and then identify if there's landscape as such, what will be the travel motions, like travel market share for each different landscape. That's the power of a deep hybrid model. So a quick summary about this work: we designed a deep hybrid model to try to integrate the data, unstructured data and the structured data and models, traditional discrete choice model and deep learning, and then the data representations, the kind of graph feature and the automatic feature. And also we have the integration is highly predictive because of the kind of information integration, and also it's interpretable. But it's not just a traditional economic interpretation. We use the images and tell economic information with the urban images. There are a couple of implications about this work, but I just try to give you a summary about the summary implication for all the work I just present. There are 2 parts. One is about the implication of 3 parts. One is the implication for the travel demand modeling community, or just a demand community in general. To be quick, basically it's just lay out a new foundation. We're using deep learning for the choice analysis. Right? It is not only a simple application of deep learning to our field, but really introduces a static learning theory. It connects the 2 frameworks through utility interpretation. Random utility maximization framework exists in deep learning. They introduce new perspective, design models like regularization, use domain knowledge to regularize deep neural networks, and then also extend this economic theory to the unstructured data, which is very intuitive to us for many years, but now we have the modeling power to do it. Skip this part. And second, it's really introduced the synergetic perspective. If I really just wear my computer science to those eyes and then try to answer questions, you could criticize that the work is a bit naive, right? You think about the architectures. There are so many different architectures. You say, well, where is the VGG transformer, all the fancy architectures, right? And the interpretation, where are those line and sharp, those common interpretation techniques in computer science field? Also regularizations, there are general purpose regularization tools. I did not use at all. But the reason why we did not use them is really we try to introduce a synergetic perspective. We still have the architecture design, but our idea is to use the utility theory, some behavior intuition to design new deep learning architectures. We still have the deep learning interpretation, but it's based on the economic interpretation, which I believe is very valuable for our transportation application and the system. And also we still have regularization, but it's regularization by domain knowledge. And lastly, I need to acknowledge all the applications are very naive in all the paper I present. We predict and analyze only travel mode choice, use survey data, and typically 10,000 data points, and the images is just very naive satellite images. But you could always think about, just use a framework to all kinds of other applications, as long as some human decisions, like choice of travel modes with using larger data set, more choice with all kind of emergent mobility, with all the choice of urban activities, location choice, energy consumption choices, or even beyond the mobility, like economic or political choices. We also put all the information on the GitHub, so we could download the code and the data to replicate our work. So last thing is this is last page. So sometimes when I think about my work, I just reflect on what McFadden had done. And then when he won the Nobel Prize in 2001, he summarized such. He says that in 1960s, they see the rapid increasing availability of survey data on individual behavior, and they use the digital computers and then develop this consumer theory. This is really the first paragraph of the summary. But when you really decompose this paragraph, you see a few components. It's a data revolution in 1960s about survey data. Now we treat those as common things, but old days, they're very new, fancy stuff. And they have the digital computers, and they try to analyze individual demand and travel. There's a new phenomenon. And meanwhile, we create discrete choice model as a new model of truth. I think these days we're facing a very interesting thing. Like it's very similar to that, but we just replace this substantial thing by like our there's the opportunity in our generation. We still have the data revolution, but now we have the big end, those unstructured data, images and languages. We have the hardware revolution as a digital computer, but now we have cloud and GPU computing. We have new phenomena emerging probabilities, and then meanwhile we have the different really to combine them into a new framework. So I believe our time is fantastic, and then we could continue this line of work built upon what I present here. That's all the friends help me from MIT, advisor, committee members, and lab mates. They really help me a lot, collect the data around the models. A lot of credits to them. Thank you very much.
Thank you so much. And we have a few questions already in the comments. Just a reminder to anybody else, if you have questions, you can post them in there.
Questions here first, or yeah, you want to? Yeah.
So I'll start with that question.
Follow.
Can you turn off the volume with the device that is the input? Because if if someone else is talking,
They can hear you. Yeah.
Yeah, you don't have to move, you can do like this. There's anything.
No, we cannot hear them.
Oh,
There's a speaker for the system.
Seriously.
Yeah, like there's speakers here, right? So the mics here are picking up what we're saying.
But usually
the speakers are not functioning to project the voice on the Zoom call.
Yeah, it's okay because I think they have it as a webinar format.
Right.
So,
Yeah, no problem.
Right.
But we can't hear.
Can we hear?
right, but the type, all the questions are typed in.
in.
So,
Okay.
so Jenny will read the questions.
Yeah.
Actually, before you, I wanted to ask about so the choices that you
I figured out just come and ask the question.
oh, I see. Oh, because you were so okay.
You're right front.
Yeah.
Please.
So let me start. Yeah. So you had a slide that kind of showed the next steps about like different types of choice applications. Or maybe the one before, the different types of choices. Given the advantages you can have with exploring more like unstructured data, right? So have you thought about like different joint choices? So like multi-dimensional choices instead of just single.
Yes, definitely. So you talk about the kind of activity-based model. We have activities and natural modes and the multi-layers.
Right.
Exactly. So I didn't talk about that's another ongoing work. So the idea is when you think about the multi-dimensional choices, it provides a hierarchy structure. You could model it with the graph structure, right? And then when you think about neural network, it's another network. And I kind of demonstrate that we have ASU, DNN. Actually, I treat the neural network as some mechanism we could impose a network design. Like tools. So we could think about how to introduce a hierarchy structure into the deep learning.
That's interesting. Yeah.
That's doable. But I think it will involve some concept called a hypergraph. So you introduce hypergraphs into the baseline neural networks, and then you can model the multi-dimensional choices. That's actually a working paper. And I plan to finish it by the end of this summer.
Okay. And then a lot of the data that you have is also in like a time series type of format, right? So like so when you're dealing with like this kind of like panel data, is that
good question? So in this work, we did not deal with the panel data. That's one important extension. People often say, the discrete choice model, we deal with the panel effects, right? Fixed effect, random effects, all kinds of stuff. But here, it did not try to explicitly model that. Even like a classical discrete choice model, when you talk about the panels and you think about the proof, is kind of asymptotically closer to a cross-section data, right? Because typically in survey data, we don't have the long time series. It's very different from spatial temporal models. But in this framework, I think we could also do it, but we need to extend this deterministic neural network to the probabilistic model, and then introduce something like a probabilistic graph to deal with the panel structure.
Daniel, do you wanna?
Oh, no.
Yeah, you got a question?
Thank you very much. I really enjoyed the presentation.
Thank you.
So going back to the complexity of that FDNN, right? I think actually it's a gift, right? Because in a sense, there are a lot of behavioral aspects that the structure of the ASU cannot capture. For example, like if we have like complementarity over a certain region of the characteristic space, or like inattention, right? So how do you sort of integrate and leverage that?
That's a very good point. In the first paper I introduced, people like reviewer raise a question: do you want to provide some like value judgment in terms regarding the irregularity of the deep learning, the behavior pattern, right? And we did not explicitly talk about that in the paper because we feel like we could provide a positive or negative evaluation, right? Positive side is really kind of relax all the constraint into discrete choice models. It lets the data and help the data to learn the framework. So it's possible that the complex like patterns, like claims might be irregular. It's kind of captured our real decision making the mechanism because we are complex animal, and now we finally have the tool to model it, right? But meanwhile, people believe there are some rules that we should not violate. Right? Like for example, in the economics, people talk about the law of demand. Like Mochi, when he talked to me, he was like, at least the demand curve should always go down. We have a higher price, even it's impossible for them to buy the goods more, right? It's impossible. It's like there's something wrong with the model as well. Yeah, that's why we start talking about regularity, behavior regularization. Right? Introduce regularization and simplify a model and achieve, if we believe there's some like behavior rule, then we need to follow, and then we still do that. That's a regulation. But besides that, and then we just let the model to learn using big data.
I see. Okay. And I guess there's another follow-up question there. So oftentimes, for example, people might worry about, okay, we want an unbiased parameter, right? So then they try to deal with endogeneity issue. So how do you think it can be integrated here?
Unbiased thing. Well, that's a term from statistic. Bias, consistency, efficiency, thing, right? And then you see when we talk about this like deep learning, it's mainly a deterministic framework. Right? We didn't even talk about the like properties of any estimator. There's no such a thing. The reason I believe is that for the current research frontier, we have not got there yet. People have started to talk about the uncertainty quantification, the uncertainty in this framework. Because when you think about the source uncertainty, there are many like uncertainty sources, right? The data uncertainty, model uncertainty, all kind of stuff. But so far, at least in our field, people have not explored that. But I know in like NeuralIPS, ICML, those like computer science conference, people has tried to combine statistical theory, information theory with deep learning.
Thank you.
Sure.
Okay, I think for the sake of time, I'm going through the detailed question more with the research first. So this researcher is asking, how do you test the performance of the model? And that I believe this is related to the second project when you're talking about the SD model and imagery model. Did you use the same area, the same city as the test set? And his follow-up question is actually related, so I'm just read them together. And how do you enhance the generalization ability of the model? For instance, just taking New York City as an example, that if we only have data from 4 areas of New York City, and 4 boroughs, I believe this person is saying, and there's no data from Staten Island, which is another borough within New York City, but we want to predict data for Staten Island. And however, the urban planning patterns of this island and compared with the other boroughs might be very different. And how do you treat that generalization ability using the model?
All right, let me answer the first question.
Sure.
First question is how to evaluate the models. Those evaluation metrics that follow the common practice, prediction accuracy, log likelihood. There are a couple of them. So we test all of them and then make our conclusions. Generalizability, in machine learning, there are 2 ways to use this term. One way to talk about generalizability is like we have the training and testing set. Somehow you train a model in the training set and then demonstrate the performance in the like testing set. That's one like generalizability, which is based on assumption that the data generating process does not change that much. Like the same data set. Another is really like transferability. Sometimes people say it's a truly generalizability. It's just that you train the model, or even test model in one domain, but then you claim that the data generating process like is drastically different in other city, and how you could transfer your model into a different context. So in terms of transferability, we have not tested it. And I'm pretty sure deep learning is not very good at transfer learning, because the reason is it's a very complex model. So let me try to move to the one slide. So you just look at slides. So let's say you train all the models, train a model with a data set in this range. In some area, the driving cost is just very low, but in another place, driving costs are very high. So you try to move the data in this range to this area, right? But when you look at the curve, it's impossible. It's transferable, right? Which means that when you just use the default deep learning, and then you hope it can be transferable, I don't think it's highly likely. But there are a lot of people working on that, like transfer learning with deep learning, deep neural networks, and then out of distribution, generalizability, and how to train them. When you have a multiple data sets from the different contexts, you put the leverage of the different data sets to improve the generalizability or transferability in your question.
There's one or two questions really kind of open-ended, so I can maybe just read one of that, which is how important is AI in the future of translation industry, and how we're just asking for some open-ended, insight from you.
Wow.
And that's a really big question, I know.
How important is I believe it's a very important to answer the question. Yeah, I think so. When you look at the current publications, at least the research frontier, people have been working using the AI a lot. All kinds of fields, right? For me, it's on the demand side, the demand modeling, and also a lot of people work on spatial temporal models, like spatial temporal data, and try to use deep learning to improve performance. And then on the supply side, how to optimize the system, how to have the real-time control with reinforcement learning. And at MIT, like Harris, we work together on that. So basically, for each subfield implementation of cities, we could see a lot of advances. So I believe it's very important. And also generative AIs, this day become very popular, but we know like about 80 years ago, we start to see the power of generative models, like again, generative reversal networks. And then I believe that's also very important for our field. Not necessarily engineering, but in like urban planning and design, it could automatically generate images. I've demonstrated that. Yeah, it will have a huge impact on industry.
Perfect. And I think that concludes today's seminar.
I think Lizzie wants to talk.
Yeah, Lizzie, do you want to talk, or you're good now?
So thank you, everybody, for joining us today, and for going a little bit over time, and for Professor Wang in particular for joining us and presenting at today's webinar. And as a reminder, a recording of this will be made available on our YouTube channel and website. And this webinar has been brought to you by C2 Smart and USDOT's University Transportation Center program. So thank you, everybody, and have a great weekend.